The Matterhorn is one of the highest and certainly the most famous mountain in the European Alps. It was created as a result of one of the most dramatic events in the geological history of the Earth, the collision of two continents. The top section of the mountain is part of the combined African-Italian continent, which was thrust up over the European continent when these two great land masses collided. Halfway down the mountain, sitting on top of the European continent, are remnants of an ocean floor, which once separated these continents. In 1912, Alfred Wegener was the first scientist to demonstrate that large continental masses move around the surface of the Earth, but he had difficulty in explaining a mechanism for this movement. Nowadays, the theory of plate tectonics suggests mechanisms capable of producing this continental drift. Sometimes, when the continental masses collide, they form mountains. These are just a mere fragment of the Alpine Himalayan belt, the largest continental collision zone on the Earth's surface. Giant Earth movements along this mountain belt have deformed the underlying continental basement and have crumpled up once horizontal sedimentary strata. These large folds in the Helvetic Alps are the end result of massive compression and shortening of the Earth's crust. Sedimentary strata have been piled up on top of each other after having been transported tens of kilometers from where they were originally deposited. Further to the south, along the Italian-Swiss border, thousands of small-scale folds reveal intense local deformation. We'll return to these outcrops in greater detail in the next program. Only careful examination of the outcrops and the construction of detailed geological maps has been able to unravel the complexities of this mountain belt.
Although the structure of the Alps is very complicated, the picture was established over 100 years ago. Like many scientific concepts, there was a key idea. This was the idea that rock masses could be transported horizontally, one over the other. This is the so-called nap theory of the Alps. The great Swiss geologist Escher von der Linth was the first person to, from his field observations, decide that this was the answer to the alpine structure. Here is one of Escher von der Linth's field notebooks, in which he records meticulously the details he observed in the field, which enabled him to develop this theory. Like many theories, there was a considerable amount of controversy at the time, and it was not universally accepted for about 40 years.
One of the earliest and most impressive demonstrations of large-scale Earth movements was made by Escher on this striking geological contact. Here in 1840, he worked out that huge volumes of rock had moved horizontally over tens of kilometers. This contact can be traced right across the high mountains and down into the valleys. And it was at this small outcrop, hidden under the trees, that Escher made his detailed observations.
In this outcrop, there are two major sedimentary units. A 250 million year old reddish sandstone on top and a much finer 50 million year old siltstone underneath. Both the rocks are the right way up, but because the older is now on top of the younger, this contact must be tectonic. Some 10 kilometers of rock have ridden in along this thrust fault, but they've produced a surprisingly narrow band of highly deformed rock. The main movements pulverize the rock into a fine-grained myelinite. And these small folds and this thin line represent just the last stages of movement.
Another important figure in alpine geology was Albert Heim. Today we are in the Earth Sciences department of the ETH in Zurich, where Heim was a professor. Heim had a remarkable ability for appreciating the geometry of structures in the Swiss mountains, and he built these rather magnificent models to illustrate this relationship. Heim also understood very well indeed the relationship between small-scale structures and large-scale structures in these folds, and he might be considered to be one of the initiators of modern structural geology.
But it's impossible to work out anything about the geological structures unless they've been exposed at the surface. Like all high mountain ranges, the Alps are heavily glaciated. This is the Aletsch Glacier, at over 25 kilometers in length, the largest in Europe. Glaciers are the most powerful method of erosion, gouging out deep U-shaped valleys and carrying large quantities of rock debris down the mountain slopes. The pinnacles, which stick out above the glaciers, are worn down by frost shattering, which breaks off blocks and boulders. These fall down onto the surface of the slow-moving glaciers. The erosion of the Alps has been going on since the rocks were first uplifted by the continental collision. They're still rising at 1 millimeter a year, with glaciers and rivers eroding down even more deeply into the geological structures. At the lowest point of the glaciers, well below the permanent snowline, the ice melts, and debris consisting of rock fragments and mineral grains is carried by the meltwaters into rivers. These rivers transport this debris out onto the surrounding plains, where it may be reworked and eventually carried out to sea to be deposited on the ocean floor. The ice-sculpted Alps now form an arcuate strip right across Central Europe. The Alps in southern Switzerland can be divided into several distinct tectonic zones. The southern zone, on the Swiss-Italian border, the Pennine zone, which includes many of the high peaks, and an outer zone called the Helvetic zone. To the north is the Molasse, a much younger basin full of conglomerates and sediments eroded down from the Alps themselves. Large areas of granitic basement were caught up in the continental collision, and some of them are now exposed at the surface by erosion. The pre-Alps are a comparatively small unit of sedimentary rocks which were thrust northwards from the Pennine zone. The boundary between the Italian and European continents is located along the contact between the Pennine zone and the rocks of the southern zone. For the rest of this program, we're going to concentrate mainly on the geological structures that are so well exposed in the Helvetic zone. These Alps are relatively free of glaciers. They form a narrow, arcuate zone over 300 kilometers long and rarely more than 40 kilometers across. The structures are wonderfully exposed in the high mountains and deep valleys. These sedimentary strata range in age from about 200 to 40 million years old and are predominantly limestones and shales, both relatively shallow water marine sediments. This pile of deformed strata is sitting on top of much older continental basement. In some areas of the Alps, the continental basement now forms some of the highest and most imposing peaks. These are the Aiguilles, part of the Mont Blanc Massif. Basement rocks are the oldest rocks in a collision zone like this, stratigraphically and tectonically beneath the deformed sedimentary strata. But these older granites and gneisses have been affected in a few places by the alpine orogeny. In the deepest valleys in the Helvetic Alps, glacial meltwaters have cut deep gorges into the basement, revealing that these old granites and gneisses have had a complex history, including being intruded by numerous dikes. The contact between the basement and the overlying sedimentary strata can be followed right across the Helvetics, and high up above the gorges, the contact is sometimes clearly exposed. Here, the top of the basement is red, showing that in the distant past, even before the Alps began to form, it was again exposed and weathered at the Earth's surface. At that time, sediments were deposited unconformably on top of the basement. But if we look higher up, we can begin to see some impressive structures formed during the Alpine mountain building event.
As a result of plate collision, a compression was set up in the basement and cover rocks, and strong folds were formed in the Mesozoic cover sediments. In this cliff of the Tour Salière, we have a good example of a large sideways closing fold in the Mesozoic strata. This is called the Morcle fold nap. For scale, the height of this cliff in the center is about 1,200 meters, and the length is about 4 kilometers. We can follow the structures by tracing the contortions in a prominent white limestone band in the Jurassic. Beginning at the top of the cliff, one sees the white limestone forming a series of Z-shaped folds forming the summit ridge of the mountain. Towards the right-hand side of the cliff, one sees more M-shaped fold structures in this limestone. Here is our white Jurassic limestone here. Clearly this part of the fold was once connected with the top part. It's just been removed by erosion, and so we can build up the overall picture of the major structure. On the base of the cliff, the limestone forms a very prominent white layer, which is almost unfolded, connected with the M-shaped folds in the front of the structure. So we can now see the complete structure of the Morcle fold nap. Clearly, this strong folding implies a very strong contraction of the cover rocks, and it also goes together with a contraction of the basement rocks. And if we look at a more regional picture, the regional structure of the Morcle nap is that of a large, sideways closing anticlinal fold. This fold has been moved over the Aiguille Rouge basement. If we go further to the south of the Morcle nap, we find that the core of this fold also contains basement rocks. These are the basement rocks of the Mont Blanc massif. At depth, these basement rocks connect with the Aiguille Rouge massif basement. So here the very strong contortions and contractions of the Mesozoic cover are going together with a strong contraction in the underlying basement materials.
To really unravel the effects of deformation in a structure such as the Morcle nap, we need to work out if the thickness of the strata has changed during deformation. And to do that, we must measure strain. Because this nap is exposed on inaccessible ground, it's often convenient to look at the small-scale geology using boulders and blocks in the scree slopes.
Conveniently for us, there are bands of conglomerates folded around the Morcle nap, and the blocks in this scree have come down from around the front of the nap. The conglomerate is just an extremely coarse sedimentary rock, but because many of the grains are rounded, we can use them for measuring strain. Up here, there's a block in which the pebbles have been highly deformed. They've been stretched out and flattened so that the ratio of their long to their short axis is 4 or 5 to 1. The shape of such pebbles, like this one, are an extremely good indication of just how much deformation has taken place. And if I plot the shapes of these pebbles on a cross-section of the Morcle Nappe, we can see that they vary from being essentially undeformed on the upper limb to being increasingly deformed as we go around the front of the nappe to the lower limb.
The nose of the Morcle Nappe points to the north. But in most of the Helvetic Alps, this nappe and others like it are exposed in west-facing cliffs, where north is on the left of the screen, and for the rest of the program, we'll examine these structures from this viewpoint. The strata in this nappe were once nearly horizontal and of roughly constant thickness. They were lying on the continental shelf, but were pushed up over a rise in the basement rocks as the two continents began to converge. As the folding started, the beds on the lower limb became inverted and began to thin out. Smaller folds were generated around the front of this nappe as it continued to move northwards. The strains created during this nappe forming process were enormous, particularly along the inverted lower limb. But it's only by looking at small-scale features, such as the pebbles, that it's been possible to measure the strain. But we also need other ways of measuring strain in case there isn't a conglomerate full of pebbles. Some of the most internally deformed beds at the base of this nappe are exposed along the sides of the Rhone Valley.
The measurement of strain is one of the key techniques for the interpretation of the tectonic structures of the Helvetic nappes. We have seen that using deformed conglomerates, it is possible to work out the stretching directions and flattening directions in these rocks. In these cliffs, in the vineyards above the Rhone Valley, we have other techniques we can use for measuring strain. In this outcrop, we have deformed belemnites. These are fossils which lived on the floor of the Jurassic Ocean. They represent the hard parts of marine animals. As a result of the tectonic deformation here, the belemnites become stretched. The dark grey particles that you see here are parts of the original belemnite, and they have become separated, and between them one finds now a filling of quartz and calcite crystals. It is possible, by making a reconstruction of these lengths, to establish the original length of the fossil. So we are able to determine the actual stretching in this particular direction. Professor Heim, over 100 years ago, discovered this technique. We also here have other methods by which we can measure strain. Here's an example of a limestone with small subspherical particles of the mineral pyrite. Now, pyrite is a very rigid mineral, and it's very resistant to deformation, whereas the limestone around is more ductile. When the rock deforms, the matrix around the pyrite pulls away from the pyrite, and the spaces, which are called pressure shadows around the pyrite, are subsequently filled by fibrous crystals of quartz and calcite. It is therefore possible, using these pressure shadows, to determine the direction of stretch in the rock, and by measuring the shapes of the pressure shadows, it is possible to get some idea of just how much deformation has taken place.
But it's also worth standing back and looking at the large-scale structures within this nappe. These cliffs are made of a distinctive limestone bed called the Ergonian limestone. Here, right at the extreme front of the nappe, this massive bed is almost vertical as it curves over from the upper limb of the nappe to the lower limb. It's nearly 100 meters thick here. As it curves into the lower limb, where it's upside down, it begins to thin out. In the Rhone Valley, the base of the Morcle comes across the hillside and into the valley floor just beside this quarry.
At the back of the quarry, there's this white band. It's not limestone, it's marble. Metamorphism has changed the original sediment into this relatively hard and ornamental rock. Yet the staggering thing is that this relatively thin band, which is what, 3-4 meters thick, represents the whole of the Ergonian limestone. Along the base of these nappes, the deformation was so intense that the Ergonian was stretched out until its original thickness was reduced by a factor of 50.
Because these nappe structures are so large, it's sometimes difficult to work out which part of the structure is which. The shape of the smaller folds around the nappe can often help this. This fold is an S-shaped fold and is on the upper limb of the nappe. The beds on the lower limb of the nappe also contain smaller asymmetric folds. This arête descends from the Dent de Morcle, the peak from which this nappe is named, and it provides an excellent opportunity for examining these folds in 3 dimensions. This fold is a Z-shaped fold, only found in the inverted beds on the lower limb. So far, we've only considered the structure of the Morcle nappe and the underlying basement in 2 dimensions. But of course, there's a 3rd dimension. These structures extend for tens of kilometers along the axis of the Helvetic Alps. The basement is lower in the center, and here erosion has yet to remove the higher structures. Above the Morcle nappe are 2 other nappes. These nappes are similar to the Morcle, but do display some important differences. The thick limestone forming this arête is the Ergonian limestone. This is folded into a massive S-fold on the upper limb of the nappe. Like all these structures, it extends for many kilometers, and the same fold is clearly visible in the next valley. But below this massive limestone, there are many thinner limestone strata interbedded with shales. Compared with a single fold in the massive limestone, these thinner beds have been folded into many small, tight and irregular folds. These are called disharmonic folds, quite different from any of the structures we saw in the Morcle nappe. The intense deformation that we've observed in these Helvetic Alps seems to have affected the underlying basement only superficially. This, together with the very large scale of most of the folds in this part of the Alps, suggests that these structures were formed at quite a high level in the Earth's crust. The only reason that we can see them is because of intense glacial erosion. These structures probably formed 5 or 10 kilometers below the surface.
The Helvetic nappes and their underlying basement form an outer zone in the Alps where the European plate is just beginning to become deformed as a result of subduction beneath the Italian plate. We are now in the Pennine Alps, where the high mountains show something else. Here we are very close to the actual plate contact, and the rocks have been very severely deformed. In our next programme, we will discuss the structures and finds in these Pennine zones.